Rates of change. From its introduction, the derivative dy dx was designed as a method of measuring the rate of change of y as x changes. In terms of graphs, this is equivalent to measuring the slope of the tangent to a curve. Any rate of change can be expressed in derivative form. For example, the rate of change of volume v as the radius r changes can be written as dv dr. The rate of change of revenue r as the quantity sold q changes can be written dr dq. The rate of change of population p as time t changes can be written dp dt. Note that if the second variable is not mentioned, then it is always assumed to be time t. For example, the rate of change of area A would be written dA dt. So time would be our second variable. So this would be differentiating A, the area, with respect to t, time, or the rate of change of the area with respect to time, or as time changes. Example: the volume, v centimeters cubed, of a rectangular box is given by v equals 3x times x plus 4 times x plus 6, where x is in centimeters. Find the rate of change of the volume as x changes when x equals 2 centimeters. So when we hear rate of change, we want to think differentiate. So we need to find dv dx, the derivative of the volume as x changes, or with respect to x. We start by simplifying v, so multiplying out the brackets. So this is the volume, so we need to multiply out the brackets. So volume is length, which is 3x, multiplied by width, which is x plus 4, multiplied by height, which is x plus 6. So length by width by height. So 3x by x plus 4 by x plus 6. So multiplying out these brackets first, we get x squared plus 10x plus 24. And then multiplying in the 3x, we get 3x cubed plus 30x squared plus 72x. So now we've simplified the volume, we want to differentiate the volume. So the derivative dv dx equals, so 3x cubed differentiates to 9x squared, plus 30x squared differentiates to 60x, and plus 70x differentiates, plus 72x differentiates to 72. So now we have the derivative. We're interested where x is equal to 2. So we swap each of those x's for 2 with brackets. So we have 9 times 2 squared plus 60 times 2 plus 72, which is 228 centimeters squared. Note that the units are the units of the volume divided by the units of x. And the units of the volume are centimeters cubed. And the units of x are centimeters, which is technically to the power 1. And centimeters cubed divided by centimeters to the power 1 is centimeters squared, because 3 minus 1 is 2. The area, a meter squared, of a region is given by a equals 8t squared plus sine 2t, where t is in seconds. Find the rate of change of the area when t is equal to pi over 2 seconds. So again, rate of change, we want to think differentiation. So the rate of change of the area is dA dt. We want to differentiate A with respect to time. Differentiate the area with respect to time t. So the area is 8t squared plus sine 2t. So the derivative of that dA dt, 8t squared differentiates to 16t. Sine 2t differentiates to cos 2t times 2. So we're using the chain rule here. So we're differentiating the sine, so we get cos 2t, we keep the angle, and then we differentiate the angle. 2t differentiates to 2, because remember we're differentiating with respect to time. And cos 2t times 2 becomes 2 cos 2t. So we get 16t plus 2 cos 2t. So now we want to sub in pi over 2 in place of t. So we get 16 times pi over 2 plus 2 times cos times 2 times pi over 2, which is just pi. And that gives us 8 pi plus 2 times minus 1, which gives us 8 pi minus 2. So we have 8 pi minus 2 meters squared per second. So this is the rate of change of the area. Two important rates of change are velocity, speed, and acceleration. Suppose a particle moves along a straight line, the x-axis, and its displacement from the origin, i.e. its location, is called x. So here we have the x-axis. Here we have 0, the origin. And here we have x. And this is the displacement from the origin. So it's moving to the right. Then velocity equals v, which is dx dt. And acceleration, which is equal to a, is dv dt. And if this is v, then we're just differentiating this again, which is the second derivative, dx squared dt squared. So velocity is the first derivative, acceleration is the second derivative. If the name of the variable representing displacement is s, then naturally the velocity would be ds dt, and the acceleration would be d squared s dt squared. Questions involving displacement, velocity, and acceleration often refer to the following concepts. So greatest or least displacement, we put the velocity equal to 0, so we put the first derivative equal to 0. Greatest or least speed or velocity, we put the acceleration equal to 0, so we put the second derivative equal to 0. In each case, we solve to find the time t and then calculate anything else that may be required. In practice, questions involving greatest or least displacement, velocity, or acceleration amount to max and min problems. Thus, if we have to distinguish between greatest and least, we can use either the first derivative test or the second derivative test. So either way, when we hear mention of velocity, acceleration, displacement, we want to think differentiate. So we have an example. The position, s meters, of a particle relative to a fixed point after t seconds given by s equals 2t cubed minus 4t squared plus 2t. So we have 4 questions about this. So remember, if we're interested in greatest or least displacement, we put velocity equal to 0, so first derivative equal to 0. And if we're interested in greatest or least speed or velocity, we put acceleration equal to 0, so second derivative equal to 0. So part 1, find the 2 times when the particle is instantaneously at rest. So if it's at rest, its velocity is equal to 0. So the particle is instantaneously at rest when the velocity is 0. So v, the velocity, is ds dt. So we're going to differentiate s with respect to t. So we're going to find the first derivative. And that's equal to 6t squared minus 8t plus 2. So the derivative of this is this. So we put this first derivative equal to 0. We put the velocity equal to 0. So we have 6t squared minus 8t plus 2 is equal to 0. We simplify by dividing across by 2. We get 3t squared minus 4t plus 1 is equal to 0. We factorize, getting 3t minus 1 multiplied by t minus 1 equals 0. And then we solve. So t is equal to a third and t is equal to 1. So remember, t represents the time. So the 2 times when the particle is instantaneously at rest is after a third seconds and 1 second. Part 2, find the acceleration after 2 seconds. So we worked out that the velocity, the first derivative, was 6t squared minus 8t plus 2. We got that in part 1. So now we want to differentiate this again. So we want to get the second derivative. So a, the acceleration, is dv dt. So we're differentiating v with respect to t. So the derivative of 6t squared is 12t. The derivative of minus 8t is minus 8. So now we have the acceleration, and we were interested in the acceleration after 2 seconds. So we swap that t for 2 with brackets. So 12 times 2 minus 8 is 16. So the acceleration after 2 seconds is 16 meters per second squared. Part 3. Find the displacement when the acceleration is 4 meters per second squared. So in part 2, we worked out that the acceleration was 12t minus 8. So we're interested when the acceleration is equal to 4. So we're going to let 12t minus 8 equal 4. So we're going to let the acceleration that we got from part 2 equal to 4, and we solve for t. So we bring the minus 8 over the equal sign, it becomes plus 8. So we have 4 plus 8, which is 12. So 12t equals 12. And dividing across by 12, we get t is equal to 1. So when t is equal to 1, so we're going to substitute 1 back into the original equation, so which is s. So we have s equals 2 times 1 squared minus 4 times 1 squared plus 2 times 1, which is equal to 0. So the displacement when the acceleration is 4 meters per second squared is 0. Part 4. Find the minimum velocity of the particle in its motion. So the minimum velocity is when the derivative, i.e. the acceleration, is 0. So it's when we have a stationary point. So for greatest or least speed or velocity, we put the acceleration equal to 0. So we said that at the start of the example. So we let a equal 0. So acceleration is 12t minus 8. So we let this equal to 0. So therefore t is going to be 8 divided by 12, which is 2 over 3. So solving for t, we get t is equal to 2 over 3. So we know that the velocity is 6t squared minus 8t plus 2. We got that in part 1. So we swap each of those t's for 2 over 3. So when t is equal to 2 over 3, v, the velocity, is equal to 6 times 2 over 3 squared minus 8 times 2 over 3 plus 2, which is minus 2 over 3 meters per second. So the minimum velocity of the particle in its motion is minus 2 over 3 meters per second.